Hi all, welcome to part 3 sequential circuits. So it's a continuation of the previous video. Please watch part 2 and come to part 3. So what we were discussing so far is the implementation of a memory element using two NOT gates. This is what we seen. Then this NOT gate, as there is no user input facility, we replaced with a NAND gate as well as NOR gate. This is a NOR gate implementation, and one of the input we are now taking from the user. Okay, that's set reset part we will see later. So that about the basic circuit. Now how this is working, so that is what you have to analyze. But before analyzing it, to make this analysis simpler, let me take some slightly different example involving just a single NOR gate or NAND gate, and we will see how it is working, and that we will generalize here. So the circuit is something like this. Before we analyze the basic latch, so we are calling it as latch, because why it is called as a latch? You know, it's actually latching some information inside, right? So just like the normal latch we are using in house and all. Okay, so some information is being kept inside that circuit. Okay, so that is the meaning of latching. So typically we call this kind of circuit as latches. So we are going to analyze this latch implementation using this NOR gate as well as NAND gate next. But before that, let's analyze some basic latch. Before this analysis of the basic, let's look at a two simpler examples with the feedback. Simply with the feedback, two examples we are trying to explain. So here it involves a NOR gate and the output is given as input. Here NAND gate, again the same feedback circuit. Okay, so let's start analyzing with this example. So what is happening here? Just understand clearly. So typically, you can call this first input as the control input. Okay, so control input means it's actually controlling the entire operation of this particular small circuit. So when you are giving 1 to this control line, I mean x, it will be having on set of on behavior, and if I am giving x is equal to 0, it will have a entirely different behavior. We will see that. And this is a data line, and data line is something taken as the as feedback, like the output is given as input, and this thing is what we call as a data line. So this is a data that is coming as a output, which I am giving as a input to the same circuit. Okay, and this is a control line. So this is a typical implementation we are having. And let's see, suppose the output at clock cycle t is given as a input, so that in the next clock cycle what is the output, so which I can denote by t plus 1. So currently at clock cycle t, at a time t, the output is like ft, and that I am giving as feedback to the same circuit, and what is the output of the circuit at time t plus 1. Okay, as a function of, so what is this f of t plus 1? This is a function of the actual input, the present input x, and the past output ft, right? That is what I want to see. And you can see this input x, and so two inputs are there, like x and ft, and you can see four combinations 0 0 0 1 1 0 1 1. So when this x is equal to 0, when this x is equal to 0, okay, when I am giving this x is equal to 0, you can see how the circuit is working based on this ft. Okay, so when this x is equal to 0, suppose this ft, the previous output is like a 0, so that is the first case. Okay, so this row I am explaining. If this is 0, what will happen? See, x is already 0, right? So this is scenario we are explaining, 0 0 case. Okay, x is 0 and this is also 0. And for NOR gate, both the inputs are 0, OR will give you 0 and its negation is NOR, right? This will give you 1. So the output ft plus 1 is found to be 1. Fine. So this is the first case. Okay, let me remove this. Now when I am applying this x to be 1, what will happen? So before that, the 0 itself, the 0 x is equal to 0 itself, but ft is 1, right? That we will see. So when you are applying ft to be 1, this NOR gate, one of the input is 1, so that the output of the NOR gate will be 0. Is that concept clear, right? Because OR operation will give you 1, negation will give you 0. So the output is found to be 0 in this case. So you can see that when you are applying ft to be 0, the previous output is 0, the present output is 1, previous output is 1, present output is 0. That means you are getting the present output as, ft plus 1 as, the complement of the past previous output. Right, now what will happen when x is equal to 1? So that is the next case, x is equal to 1. So when x is equal to 1, see, suppose this is 0, what will happen? or this can be 1. Now tell me whether this is 0 or 1. Irrespective of that, one of the input of this NOR gate is 1. Okay, so you don't worry about this input, let it be anything. Okay, whatever it is, one of the input is 1 means the OR gate will give you 1, whether the other input is 1 or 0. Okay, that irrespective of that, this OR gate will give you 1, and in negation of that will be 0. Right, that means the circuit is always giving you 0 whether this ft is 0 or 1, provided this x is 1. Is this concept clear? This is very important understanding here, right, especially for this circuit. So this part is fine, but this is more relevant part. I mean, this is more relevant. What I want to say is this speciality of this NOR gate, whenever one of the input is 1, you don't look at the other input, always the output will be 0. Let the other input be 0 or 1. Don't care. Let the other input be 0 or 1, the output is always 0. This 0 will be dominated, right? So the whole thing. So you don't worry about this one, whether it is 0 or 1, whatever it is, whether, right? The output will be 0 fixed. So this understanding is what is needed for me. So that is what is written. So this control line, data line. But you can see, if a NOR gate control line is 0. So control line is 0 is the first case we observed. Then that NOR gate negates a data line. Right, we saw like you are getting ft is equal to ft plus 1 is equal to ft complement. The negation is happening. When the control line is 1, so that is the second case, right? When x is equal to 1, you can see that the NOR gate output is driven to 0, ignoring data line. The data line, whatever be the input in data line, that is fully ignored. The second case you have to keep in mind, suppose this x is equal to 1, whatever it is, let me write it as d, whether it is 0 or 1, whatever it is, the output is always 0. Right, so it is always giving you 0. Simply this data line is being ignored, right? So this is what is needed for me. In a similar way, let's analyze this same feedback circuit using a NAND gate, and what you can see here, here it is like when this x is equal to 0, that ignoring part is happening, because whether this one is, let me write it as d, that means whether this one is 0 or 1, whatever it is, right, one of the input of this circuit is 0 means this is NAND, right? So and negation. So one of the input is 0 means the AND operation is going to give you 0 for sure, and its negation will give you 1. So always a circuit will give you 1 as the output irrespective of the other input. We'll let the other input GT can be 0 or 1, whatever it is, the output will be 1 when provided the control input is 0. So this is again very important observation, right? Now the other case is like suppose you are giving this x as 1. When you are giving x as 1, that you have to observe, like here if you are getting 0, you know, AND gate 0 and NOT gate will give you 1, you are getting it as 0. Now instead of that, here this input is 1, AND will give you 1, and this negation will give you 0. So depending on that, and you can see that that is nothing but this GT complement, okay, like this. So when the control input is having a value 1, the data input is ignored in NAND gate implementation like this, where in NOR gate implementation, when the control input is 0, the data input is ignored. And now what about the other case, that is just negation of the past output, okay. So that is irrelevant here. So this is only that what matters when this is some don't care, don't care what I mean. When this input is 0 or 1, the output is showing you as 0, right, fixed. Yeah, that about it. So this is a key observation we are having. If an AND's control input is 1, then the NAND just negates the data line, okay. But when the control input is 0, then the NAND's output is always like a 1, ignoring the data line. Whatever be the input in the data line, it will give you 0. Yeah, thanks for watching, and this is going to help you on the analysis of the actual latch implementation using NAND and NOR. Okay, so this is just an intermediate video. We will continue the actual analysis of the latch circuit in the next video. So this observation only matters, like when you are having a circuit with a NAND gate like this, the one of the control input equal to 0 matters. When the control input is 0, the circuit is just giving you 1 irrespective of the data line, where in NOR gate implementation the circuit is giving you a 0 irrespective of the data line when the control input is 1. Okay, so that you have to keep in mind. Yeah, I'll see you in the next video.